Okay, so let's try some more example problems on basic derivatives before we get to the chain rule. And once again, we'll be working with these properties and identities, and the basic method is going to be algebraic manipulation first, then apply the properties, then apply the identities, and lastly simplify with a little bit more algebraic manipulation. Okay, so let's say we're given this function, q of a is equal to 5 times sine squared a plus 5 times cosine squared of a. Find q prime of a. Notice that I'm using slightly different notation for the derivative than I did in my last presentation, and the reason I'm doing this is just to get you familiar with the various different notations in calculus. So if we were to write this out, q prime of a, oops, wrong color. Alright, so the solution is going to be in red. So q prime of a is equal to, and there's various ways of writing this. You could say, open parentheses, 5 times sine squared of a plus 5 times cosine squared of a, and then put the prime part outside of that. That can be a little subtle and hard to read. Personally, what I prefer to do is to write it this way. So as an alternative, you could write it this way as d dA of the quantity 5 times the sine squared a plus 5 times the cosine squared of a. Either of these notations are acceptable. So anyway, using this notation, let's continue. Again, first things first, algebraic manipulation. You notice you have a common factor. Both of the fives, both of the trig functions are multiplied by 5. So your q, wow, that is an ugly q. Let's try that again. There we go. Q prime of a is going to be equal to, now since we're just doing an algebraic manipulation, everything is going to stay inside of the derivative function. Okay, so like I said, we factored the common factor out. We pulled the 5 out of the trig function, but not out of the derivative function. The derivative still applies here just the same way it applies here. Alright, now as you've probably noticed already, sine squared plus cosine squared is 1. So effectively what this really is q prime of a is equal to the derivative with respect to a of 5 times 1. 5 times 1, I sure hope you can do that. And okay, so now we've got it down to the point where it's as simple as we can get. Let's check our identities. 5 is a constant, so this identity will apply. We'll get rid of the derivative symbol using this identity. And the derivative of a constant is 0. So we started with this whole complicated function up here, and it turns out to be that really simple solution. Okay, let's try something else. Derivative with respect to time, or with respect to t of, oh wait a minute, there's a slight problem here. Let me fix that. Okay, I changed the variable from x to t. Alright, so that's really ugly penmanship, but hopefully you get the point. Alright, now we don't have an identity that gives us derivative of the natural log of some complicated function of x. We do, however, have this identity that gives us natural derivative of the natural log of x or t or whatever your independent variable is. So let's see if we can do some manipulation so that this complicated stuff inside the natural log function gets a lot simpler. Alright, so I said previously that when you're dividing inside of a natural log function, that's the same thing as subtracting. Well, if that's true, then it should also make sense that if you're multiplying inside a logarithm, that's the same thing as adding outside the logarithm. So in other words, if you want to put it in general terms, if you have the natural log of the quantity AB, that is equal to the natural log of A plus the natural log of B. So applying that to this function, we have 2 times e to the t. So we'll separate those out, and we'll still keep this 20 over here. Can't forget about that. So we'll keep, and the derivative operation. So we'll get d dt of, let's see, quantity 20 times natural log of 2 plus the natural log of e to the t power. Alright, and like I said, all we did is we separated the gold stuff. That became that. From the blue stuff, that became that. And the red stuff over here stuck around. Okay. Hopefully you saw that. Natural log of e to the t. That's just t. So rewrite this derivative with respect to t of the quantity 20 times the natural log of 2 plus t. Okay, now we just distribute the 20. Notice all we're doing so far is stuff pretty much just Algebra 2 style manipulations. This is 20 times the natural log of 2 plus 20 times t. Alright, we've done as much algebra as we can now. Now what we need to do is distribute the d dt to here and here. In other words, we are using this identity, that the derivative of a sum is the sum of the derivatives. Okay. So this becomes the derivative of 20 times the natural log of 2 plus the derivative of 20 t. Well, 20 times natural log of 2, so looking at this part, 20 times natural log of 2, there's no t's in there. And that means that 20 times natural log of 2 is a constant, derivative of a constant is 0, so this whole part becomes 0. So all we're left with then, and I'm going to continue my work over here, is the derivative of 20t. 20 is a constant, so we can move it outside the derivative. We got 20 times the derivative of t, otherwise known as t to the first power. T to the first power, we can apply the power rule to that, except instead of x's, we got t's. So what we do is we take the 1, move it out in front of the t, and decrease the exponent by 1. So we got 20 times 1 times t to the 1 minus 1, and t to the 1 minus 1 is 0, 0 to the 0th power, t to the 0th power is 1, so this is going to be 20 times 1 times 1, which is the same thing as 20. Okay, you're not always going to be able to get rid of all the t's, but remember, that's not your goal. Your goal is to get rid of the derivative symbols. Okay, next problem. Going to start moving a little faster here. Alright, so you got an unusual logarithm here. It's a log base 5. We don't have an identity for that. And furthermore, just to make things really nice and complicated, we got this 25 times p, not just p. So there's two complications here. We have an unusual base, and we have natural log of a product involving our independent variable. So first things first, hopefully you remember the change of base formula, where if you have log base b of a, this is the same thing as log base c of a divided by log base c of b. And also remember that log base e of x, actually no, that's alright, yeah, log base e of x is the same thing as the natural log of x. In other words, as long as you can convert your base to e's, then you have ln x's, and we have identities that apply to ln x. So we're going to do a change of base, and we're going to change our base from 5 to e. And we're not doing anything with the derivative symbol yet. So, like I said, algebraic manipulation first, then you apply your derivative properties, then you apply your derivative identities, and then you simplify. Alright, so ddp of, let's see, this is going to be, oops, not log, we're changing it to log base e, which is the same thing as natural log. So this is going to be the natural log of 25p divided by the natural log of 5. Actually, you know what? There's an easier way to do this. This will work. This approach will work, but there's an easier way to do this. We use the product of logs first. So, just to remind you how the products of logs work, if you have logarithm of ab, That's the same thing as the log of A plus the log of B. I just remembered there's a reason I chose that 25 there, because 25 is 5 squared. Okay, let's start over again. Even though, like I said, that approach would eventually work, there is a easier way. Alright, so applying this property first, the product rule of logarithms, and again, still not doing anything with the derivative. Okay, log base 5 of 25, that becomes 2. So this is going to be DDP of 2 plus log base 5 of P. And so now probably the best thing to do is to distribute the derivatives. And we're going to have to do a little bit more algebra. So whether you do more algebra first or you distribute the derivatives, it's completely up to you. But I'm doing this because I kind of suck with this stylus still. And I can see that if I play my cards right here, I will have less writing to do. Alright, so I distributed the derivative across the two terms that are added together, one of which is a constant. Derivative of 2 is 0, as is the derivative of any constant. So all we are left with now is the derivative with respect to P of log base 5 of P. Okay, now we can apply the change of base formula. And again, a lot of these steps, it really doesn't matter exactly what order you do them in, but you do have to do all of these at one point or another. Okay, so we're going to carry on over here. And this is going to be DDP of the natural log of P divided by the natural log of 5. Natural log of 5 is a constant, so you can move that constant outside of the derivative. And we are almost done. Derivative of natural log of P, we got an identity that looks like that. It's that one. Except instead of x's, we got p's. But since we got a p there and a p there, and that just represents a change in our independent variable. Oops. So, natural derivative with respect to p of the natural log of p is just 1 over p. So this is going to be 1 over the natural log of 5. Wow, that is an ugly 5. Times 1 over p, which is the same thing as 1 over p times the natural log of 5. And that is your answer. Next up, we got this cosine function. Now, might be the first time you've seen this, but this symbol here, that is the Greek letter theta. It is very often used for angles. You will see it a lot in physics. So, we got this derivative with respect, g of theta is 4 times cosine theta. Find dg d theta. This is a pretty easy one, so let's just plow through it. So we got dg d theta is going to equal d d theta of the function g, which is 4, times the cosine of theta. Okay, take the 4, move it outside. It's going to be 4 times the derivative with respect to theta of cosine theta. And the derivative of cosine theta, going back to our functions over here, derivative of cosine is negative sine. And so we get 4 times the quantity negative sine theta, and so this becomes negative 4 sine theta. Alright, that was a pretty easy one. Okay, got trig functions galore here. P of t is equal to sine of t cosine t. Oh, I forgot to ask you a question. So let's say the question is find dp dt. Okay. Hopefully you remember from your trig functions of Algebra 2 that the cotangent, or precalculus, whatever you saw more in, cotangent of t is equal to 1 over the tangent of t. And so that means that the cotangent of t is equal to the cosine of t divided by the sine of t. Okay, so wherever we see cotangent of t, we can put in this fraction, so let's go ahead and do that. dp dt is equal to the derivative with respect to t of sine of t. Okay, so we kept that part the same, and actually I'm going to put some brackets in here just so that it's clear what the derivative applies to, times the alright, so we got the sine of t times the cotangent of t, which is going to be cosine of t divided by the sine of t. Well, as you probably are already noticing, sine of t on top, sine of t on bottom, those cancel out. Oops, I missed the parentheses on the sine of t. Okay, those cancel out. And so what you're left with is dp dt of the derivative with respect to t of cosine of t. If you want, you can keep the brackets. It's kind of unnecessary at this point. So the derivative of p is negative sine t. Okay. Do I have another sample problem? I don't think so. Nope, that's it. Okay. Hopefully these were useful sample problems. That's going to be it before and the next thing up is going to be the chain rule.